Hi everyone, I'm Anshul Gowda and my teammates Abhay and Aryan, and today we'll be talking about the topic ion colony optimization, which is a bio-inspired algorithm that comes under the nature-inspired computing concept. This concept is inspired by how real ant colonies behave in nature, especially how they collectively find the shortest path to the food. Next. Ant colony optimization is inspired by the simple yet powerful behavior of ants. Ants do not communicate verbally, they use pheromones, which are chemical trails left on the ground. When ants walk, they deposit these pheromones. Over time, the shortest path collect the more pheromones because ants travel with them faster and more frequently. Other ants can smell these stronger pheromone trails and are more likely to follow them. As a result, the entire colony gradually converges on the shortest and the most efficient path. This natural system shows how simple agents working without central control can solve complex organization problems, which is exactly what ACO algorithm mimics. And, and communication, the pheromone system. Ants communicate using pheromones, which are chemical signals. They detect these pheromones using their antenna, which act like sensors. When ants walk, they leave pheromone trails on the soil. Other ants follow these trails, which help them find food in return for nest safety. Why this matters for ACO? Pheromone communication is a biological inspiration behind the pheromone update mechanism in the ACO algorithm. In ACO, pheromone levels on path to tell artificial ants which solutions are promising. Next. How ants find the shortest path? So first is by random exploration. At first, ants wander randomly in different directions. Each ant leaves behind a small amount of pheromone. Second, food discovery. When an ant finds food in return for the colony and reinforces the trail by laying more pheromone, this increases the strength of the path. Strong third, the strongest trails on the shortest path. Stronger paths and traveled more frequently, so they build up pheromone faster. As a result, pheromone increases, more ants start choosing the same path. And the fourth, optimal path convergence. Eventually, almost all the ants follow the same path. The one which has the shortest and has the strongest pheromone concentration. This natural optimization process is directly converted into ACO algorithm. So how is this linked to computing? These steps are exactly how ACO algorithms search for the optimal solution. The next slide will be explained by my teammate.
SEO algorithm step by step. Here we have 6 steps. Here we model what real ants do into an algorithm. First we initialize the values, then ant build solution, calculate results, update best solution, update pheromones, and finally display the answer. So here you can see initialize parameter. We have population size, maximum, and tau, alpha, beta, rho. Then we have ant solution construction, then compute fitness, then update best solution, offline pheromone update, and display result. Next, we have detailed steps of ACO algorithm. First, initializing parameter. So first we set up constants and variable like the number of ants, maximum iteration, initial pheromone, evaporation rate, and then we carefully select impact, convergence, speed, and solution quality. Then we have ant solution construction. Here each ant independently builds a solution by probabilistically selecting nodes based on pheromone trails. Then we compute fitness. Here with the help of the objective function, we will compute the fitness values. Then we have update best solution step. Here we compare each new solution to the current global best. If better, update the global best. If not, we'll leave it as it is. Then offline pheromone update. This core learning mechanism adjusts pheromone trails based on solution quality consisting of two processes. First is pheromone evaporation and second is pheromone reinforcement. The pheromone evaporation trails on all edges are reduced, preventing stagnation. And pheromone reinforcement, the best ants deposit pheromones on their paths, strengthening good roots, and then displaying the result. Upon reaching maximum iteration or convergence, the algorithm outputs the globally best solution. This includes the most efficient path and its associated fitness value. Next, advantages and limitations will be explained by Aryan.
Advantages and limitations. ACO has some important advantages. First, It often provides better solution with fewer iterations compared to traditional algorithms. This makes it useful when we need efficient results quickly. Another strength is that ACO is excellent for pathfinding problems, especially those represented as graphs, such as transport system, routing or network optimization. However, ACO also has limitations. It is parameter sensitive, meaning all algorithm needs careful tuning to perform well. Small changes in parameters like pheromone evaporation or exploration can affect the outcome. Also, for very large or complex problems, ACO may require high computational cost, which can make it slower. Next, ACO and the traveling salesman problem. A common example where ACO is used to traveling salesman problem. Here, the goal is to find the shortest route that visits all cities exactly once and returns to the starting point. If we try every possible route using brute force, the number of combinations grows extremely fast. Even five cities already give 12 possible routes. Instead of checking all possibilities, ACO simulates how ants explore paths and reinforce shorter routes using virtual pheromones. This allows the algorithm to quickly find near optimal solution much faster than brute force methods. Next. Key takeaways to summarize, ACO is a bio-inspired algorithm that mimics how ants communicate through pheromones to find efficient paths. The key ideas behind it are pheromones dynamics, probabilistic decision making, and iterative learning. Although parameter tuning and computation can be challenging, ACO remains a powerful method for solving complex optimization problems. Thank you.